Okay, these are the example problems for the first half of Lesson 7. This covers the topics of stress concentrations, normal and shear stresses on an inclined plane, biaxial bending, and then okay, so this is example 11:15. A 1 millimeter long flat bar, 75 millimeters wide by 6 millimeters thick, has a circular hole, 25 millimeters in diameter, centrally located with an allowable stress of 165 MPa. Calculate the axial tensile stress load that may be applied to the bar. Okay, so here's what's given. We've got the flat bar dimensions, we've got the hole dimensions, and we got an allowable normal stress. Okay, so R, which is the radius of the hole, is 12.5 millimeters. D, which is the net width of the bar at the hole, would be the 75 millimeters wide minus the diameter of the hole equals 50 millimeters. That's the net width. R over D equals 0.25. Okay, so once we have 0.25, we can look at our chart. 0.25, I've got it drawn right here. I'm going to follow 0.25 up until I intersect the line for the circular hole, and then I'm going to read off over here on the y-axis what the K factor is. In this case, it's about 2.3. So that's how we read figure 11:14. The net area is going to be the net area of the bar minus the area of the hole, which would be the 6 millimeters wide times 75 minus the 25 millimeters for the diameter of the hole, and I get 300 millimeters square. The allowable stress, therefore, is 165 MPAs, which equals this equation here, K times P over A net. The A net would be the area right here, like I'm saying. Okay, we solve that for P, and I get 21.5 kilonewtons. So that would be the allowable load based on the stress concentration factor. Okay, so what we're looking for is that the stress doesn't exceed the maximum stress, and we're acknowledging that the maximum stress is actually going to be higher than the normally distributed stress because of the stress concentration factor. Okay, so the next one is example 11:18. It talks about the stress on an inclined plane. I've included this graphic right here because it shows the two equations that we're going to use, equation 11.12 and equation 11.11, which means that if we have this just an axially loaded bar, and if we were to consider a stress element that would be oriented in an inclined plane, what would be, first of all, the normal stresses on that inclined plane, and what would be the shear stresses on that inclined plane? Okay, so we're given a steel bar. It's a diameter of 12.83 millimeters, and it has an axial load of 45 kilonewtons. Find the maximum shear stress and the tensile stress at that plane. So the shear stress we know is maximum at 45 degrees. That was covered in the discussion in the lesson. The area of our bar is pi over 4d squared, which is 129 millimeters squared. We have our two equations. We just have our two equations. Equation 11:11 for our shear stresses, and equation 11:12 for our normal stresses at that plane. The theta that goes in here is this angle at which we're considered the inclined plane. Okay, so when we do that, we find out that our maximum shear stress is going to be at 45 degrees, and it's 174 megapascals. And then when we calculate what our maximum normal stress is at that plane, it's also 174 megapascals. Okay, so the next problem is the biaxial bending problem from chapter 17, example 17.1. We have a simple beam. The beam is actually supported on a 15-degree angle here and is loaded as shown. The line of action of the 16 kilonewton load passes through the centroid of the cross section. Determine the bending stress at the flange tips, these 1, 2, 3, and 4. Neglect the weight of the beam. Okay, for the solution, we're going to go into Appendix A, and we're going to find out what the section modulus of this W310-202 beam is going to be. So our section modulus in the x direction is 3,050 times 10 to the third millimeters cubed, and our section modulus in the y direction is 1050 times 10 to the third millimeters cubed. Then we're going to calculate what our components are of P in the x and y directions. That's done right here. So we got P sine 15 and P cosine 15. So Px is 4.14 kilonewtons, and then Py is 15.45. We can go to Appendix H now, and based on this loading here, we can look at what the maximum moment's going to be, and that maximum moment's actually going to be right in the middle of the beam, because our maximum moment's where we're going to have our highest stresses. So we calculate the moment in both the x direction and in the y direction. And then here is our formula. F max equals plus mx sx plus or minus, plus or minus, plus or minus. Okay, so then now it's a matter of figuring out which ones are the pluses and which ones are the minuses. I want you to go take a look at how we did that. But here is the results, and here is the resultant. Again, we're going to do this by superposition. We're going to say that, hey, the stresses due to bending in the x direction plus the stresses due to bending in the y direction is going to equal the normal stress. That's essentially what superposition says. Okay, so our last problem that we're going to look at is example 17.2, and it's a superposition problem. What we're having here is a combined bending and axial loading on a beam. So by superposition, we're going to say that, this equals this plus that when we're talking about the stresses. So again, we're talking about a W14 by 61 beam. If I look that up in Appendix A, I'll find that the area is 17.9 square inches. The section moment of inertia in the x direction is 640 inches to the fourth, and the section modulus in the x direction is 92.1. The max load is going to be max moment's going to be at the middle. I calculated that as 75 kipfoot, and then our force max equals plus P over A plus or minus M over S, and here we have our equations and our solutions. Okay, thank you.